Okay, before lunch, we wrote down the definition of similar polygons. So here's your next page of notes then. Similarity statement is like our congruent statement that we had back in that chapter. For these two triangles, we're saying that triangle ABC, what do we say that this symbol means? Is similar to triangle MNO. Now, the way that we matched those up when we were doing congruence is the same thing that you have to do with the similarity. It sometimes is harder to match it with similarity than it is with congruence because the shapes are not always the same size. So you can't visually be matching them as easily. But it still means the same kind of matching. So what angles would be congruent? It's not that they're similar, they're actually the same. So the angles that would be the same, Lizzie? Okay, angle A is going to be actually congruent to angle M. Angle B is congruent to angle N. And angle C is congruent to angle O. And notice I did use the congruent symbols. Because to be similar, they have to have the same angles. Their sides are in proportion. So proportions from yesterday, ratios that are equal. So when we do the statement of proportionality, what that means is give me the ratios and state that they're all equal. So here's what we would do, and this will look a lot different than what we did in congruences. Okay, so side AB, it's not that it's going to be equal to MN, it's going to be in comparison to MN. So that ratio will equal side BC compared to side NO and side CA compared to side OM. So where did I get which ones to compare? Same thing we did with congruence. AB with MN, BC with NO, CA with OM. It's just that they are not congruent, they're in a ratio. All the ratios are equal, that's why it's called a statement of proportionality. So once we get going in the chapter, students usually forget what these directions mean. If it says to give a similarity statement, this is the kind of thing we're looking for, similarity statement. If it's asking for a statement of proportionality, this is the type of thing we're looking for. All right, everybody got those notes down? No. Not yet? And while we're waiting a little bit, I'm going to mark some angles. So angle A is the same as angle M. Angle B is the same as angle N. Angle C is the same as angle O. The sides are not equal. AB maybe is 4, and let's make MN 2. So what relationship did I establish with the sides? I'm going to make the left-hand one twice as big as the right-hand one. So 4, I should have used a number I can do. I guess I can. I was thinking it was a right triangle, it's not. Okay, if I go 8 here, then this side was 4. And to make a triangle, let's say this one was, it has to be bigger than 8. So 10, and this side would be 5. So the sides are not the same, but if I look at the ratios, each of them reduces 2 to 1. 4 to 2 is 2 to 1. 8 to 4 is 2 to 1. And the 5 is 2 to 1. So that's the idea of the statement of proportionality. Okay, did I wait long enough? Yes. I have a lot of no-name papers. Oh, great. Okay, just to let me know. So they'll be having zeros and wondering why they didn't get their points. Okay, so you might think back if you didn't have your name on it. Okay, scale factor. The scale factor is the ratio of the lengths of two corresponding sides for similar polygons. So what I was just doing with you looking at the sides that matched up and what their ratio is, that is what the statement, or that's what the scale factor is. So this looks like maybe it's about 3 times as big. So if this is 4, 3, and 6, then this side is 12. Right now, I guess if I show you enough information, you could come up with the scale factor. All you'd have to do to determine the scale factor is which side does the 12 match with. 4. It is the 4. Now, I could have made it so it flips over, but I didn't. So don't think it's always sitting in the same way. So the scale factor could be 4 to 12. It could be 12 to 4. Depends which way I want to ask it. If the problem just says, give me the scale factor, I would take either of those as a correct answer. Now, some of them say, give me the scale factor of figure A to figure B. So which one's the correct one if I say figure A compared to figure B? The 4/12 is the right one. If it says scale factor of B to A, then it's the 12/4. Now, you could reduce these. What's that reduced to be? 1/3? And this one could be 3 to 1. So let's always try and reduce the scale factors. Sometimes you won't be able to, but try to reduce. So I didn't even need all the sides of B. I just needed the correct one to match with the small triangle. So that's this idea of a scale factor. Anyone still need the notes? Okay. So here's some practice problems. Determine whether the polygons are similar, so we're going to do a yes or a no. If they are similar, write a similarity statement and find the scale factor figure B to figure A. Okay, so 2 things we have to do to determine if they're similar. Look at angles and then look at sides. What has to be true about the angles? They all have to match up. Okay, in this one, that matching is easy because any 90 from here will match with the 90 over there. So the angles pass the test. Sides. What do we have to check? The ratios. Now, which sides should you compare? In the rectangles, you should compare the short side to the short side. Okay, so maybe 4 to 10. And then the longer side to the longer side, 22. We have to figure out if those two are the same. Reduce 4 to 10. What can you divide by? Divide by 2. Dividing 4 by 2, dividing 10 by 2, that reduces to 2/5. Okay, how about 10 and 22? Can you reduce that? Divide by 2 again. 5/11. Okay, are those 2 ratios equal? No, so what's that mean? They're not similar. They both are rectangles, but one's maybe longer and skinnier in relationship than the other one is. So those were not similar. So there's no way we can do a scale factor because it's different depending upon what sides you have. Understand that one? Okay, let's try another one. Determine whether they're similar. Again, we'll do things if they are. Angles. Does every angle of figure A have a matching angle in B that's the same? Yes. Okay, sides. 5 from here. Which one should I compare to over there? It really doesn't even matter, does it? These are all 5s, those are all 9s. So no matter which sides you compare, isn't it 5 to 9? For all of them? Are these two figures similar? Yes. Okay, so now let's do what it says. If they are, write a similarity statement. What's that mean? Let's look back. What that means is this kind of thing, naming the figures how they match. They're not triangles in the one we're on, so we would just list them. What if I call this one G, D, E, F? Is similar to R, Y, W, T. There could be other correct answers because it could be turned or flipped and still match, but that one would be okay. And find the scale factor of figure B to figure A. Is that what I did here? Was this comparing figure B to figure A? No, this was figure A to figure B. So I need to go figure B to A. So B's side measurement is 9. The matching side from figure A is 5. So, and no matter which side I use, it's that. Can I reduce 9 to 5? We don't want a mixed number, that doesn't work in ratios. So there's our scale factor, 9 to 5. Thumbs up or down? Okay. So you do this one, grab your marker board. No name on it, Ben. There's your name on it. Oh, there's not a copy of somebody else's. Oh, just left them on. Let's see, I think this might be a 2-page. Oh, I see. Why don't I put your scale factors in there? Looks like if it's a yes, you would have a hard time doing this problem. So what do we want? R, S, T, M, P, L. In case you need the corner points to do a similarity statement. I'm seeing some no's and I'm seeing some yeses. Let's see if we agree. Okay, similar. Do we have an angle in figure A that always matches with an angle in B? Do we have one that's marked like that?
Yeah.
Yeah. Do we have one that's marked like that?
Yeah.
One that's marked like that? Okay, the angles work. Sides, 8, which is between those two, would match with the 4. I'm going to write 8 to 4. Okay, then 14 would be with the 7. And the 10 would go with the 5. Each of those reduce 2 to 1, don't they? Okay, so are they similar? Yes. So go in the back. What were you coming up? Why were you coming up with no? Yeah, if you were thinking R has to match with M just by like turning it, no, that's not how these match. This one would really flip over and shrink in order to match. So I'm getting a yes. So what's a similarity statement? I could go triangle RST is similar to triangle. Now match it up in the order I started. What goes with R? P, L, and then M. LM. And the scale factor of figure B to A was my 2 to 1 from figure B to A. No, I did A to B, didn't I? So I need to flip it over. Okay, so my scale factor should have been 1 to 2 to answer the question. Questions? Okay, this is a little bit different problem. It's not asking are they similar, it's saying they are similar. So I'm telling you they are, even if the pictures don't look very good. It says find the value of the variable, show the proportion used. Is the variable on a side or an angle? A side. Okay, side HJ. I need to figure out what side it matches with over here. Now looking is hard to tell. Look at this statement. HJ is going to match with RS. Okay, so it's not that it has to equal 8, but it needs to be in a proportion. Equal ratios. So x to 8 is going to be the same as, I need 2 more sides that match up. So pick another side from here.
3 to 5.
3. Does that go with 5 correctly? I'm looking here. HK, TR. So yes, 5. 3 to 5. Could I have used 6 and 10 instead? Yes, you could. So I'm just setting up the comparison of the sides. X to 8 would be the same as 3 to 5. How do I figure out what x is? Yesterday's lesson. Cross multiply. Cross multiply. So 5 times x would equal 8 times 3. 8 times 3 is 24 divided by 5. 4.8. You are going to get some decimals. So x would have to be 4.8 in order to have those be similar. All right, now you find the value of the variable. Two trapezoids to look at instead of triangles. And let's see, let me just mark some angles since I didn't write out the similarity. We'll make those the same, these the same. Would that help you know what matches? Figure out the value of the variable. All right, that one, x is 13. Okay, what are you setting up? What you got?
Let's say you had 8 or 9 over 18.
Okay, if she had 9 over 18,
Before you multiply,
can you reduce that? Sure, she can. Yep. So 9 over 18 is the same as x over 26. So you're asking, could you go 1 over 2 is equal to x over 26?
Okay, yep, I was
Okay.
wondering.
And I think, did most of you just use it the way it was?
Yeah.
But this one mentally is probably easier to do, 26 divided by 2. So 13 was the answer, no matter which one you cross multiply. Did anyone go 18 over 9? Put the 18 on top? Nobody did that? You could. You could have 18 over 9 equals 26 over x. It still will cross multiply the same. You know what you did? Okay, find the value of the variable on the similar rectangles. Show the proportions used. They're rectangles, so do I need to draw any angles in? Probably wouldn't have to. It's a rectangle. Yep, they're over 90s. Transfer up in that corner.
Yeah, it's right next to.
All right, that one ended up being 3.6. Okay, a way to set it up, 9 over x equals 15 over 6. And you're cross multiplying. So the way I did it, I would have 54 equals 15x divided by 15. And hopefully I've got the right numbers, 4.8. No, 3.6 was this one. Was 4.8 the last one before that? No? So where am I coming up with 4.8? I don't know. Popped into my head. Okay, now let's find the perimeter of each rectangle. Because I want to see if we have a ratio of the sides, is the ratio of the perimeters the same? And let's check it out. Okay, so find the scale factor of the sides. What scale factor mean? That's really the same as those ratios you were doing. It doesn't say A to B or B to A, so do you want to go big one to small one? Is that good enough? Okay, scale factor would either be 9 to 3 or 15 to 5. What's that reduced to be? No, not 1/3. 3 to 1. 3 over 1. Okay. Okay, now let's find the ratio of perimeters. Let's find the perimeter of each one and see what their ratios are. Okay, what's the perimeter here? 15 plus 9 plus 15 plus 9, 48. Okay, perimeter here, 5 plus 3 plus 5 plus 3, 16. Okay, so if we compare the perimeters, we've got 48 compared to 16. Is that reduced down? If you divide by 4, that would be 12 and 4.
You could do it again by 4.
Do it again by 4.
3 over 1.
3 to 1. Notice it came out the same as our scale factor. If every side is 3 times as big, when you add up, the total will be 3 times as big. So your scale factor is always going to be the same as the ratio of the perimeter. And that is a theorem that we'll do, and then we'll come back to those. Okay, the theorem that ends that part of our lesson is about the perimeters of similar polygons. So we need to switch from reviewing. Perimeters of similar polygons. If two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding sides. Two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding sides. Let's set up an example to go with that. Okay, so what's the ratio of the sides? I take a side from the first one, 6, compared to 9, or 8 compared to 12, or 10 compared to 15. What do those all reduce to be? Not 1/3. 2/3? Okay, so the sides are in the ratio 2 to 3. Now let's compare the perimeters. So we see how the theorem works. What's the perimeter of the first one? We added already 24. What's the perimeter of the second one? 36. So if I compare the perimeters in a ratio, if I compare 24 to 36, what does that reduce to be? That's dividing by 6 would get you to 4 ninths. No. 4 sixths, sorry, not 4 ninths. If I divide by 6, it'd be 4 sixths. You can go further though. 2/3. So if you would have divided by 12 in the beginning, it would get there. So the theorem is saying if these two polygons are similar, then the ratio of their perimeters, which reduced to 2/3, is equal to the ratio of the sides, which reduced to be 2/3. So if you know the theorem, there's some homework problems that you can get the ratio real quickly. If you don't quite understand what's going on the theorem, you'll have to find each perimeter and then make the ratio. Okay, question on that theorem? I'm going to go back to one of those examples that I skipped over. Then we'll do some more drawing type things. Okay. So I don't know if we have to find the perimeters or not. What's the scale factor of the sides? 8 to 2 or 12 to 3. Both of those reduce? 4 over 1. So what's the ratio of perimeters? 4/1. How do I know it's 4/1? Well, that theorem tells me that the ratio of the sides, the scale factor, and the ratio of perimeters is the same. If you don't believe that, add up. 12 and 8, that's 20, and 12 is 32, and 12 is 44. Perimeter here would be 5, 6, 7, 8, 9, 10, 11. So a perimeter of 44 compared to a perimeter of 11, 4/1. Okay, that's the lesson on similar polygons. And we're going to do some drawing today. We're going to do some dilations. That's why you needed to get your ruler packet. So what's a dilation? Well, it's basically a scale figure. We're going to make something bigger or smaller. We'll eventually do a scale drawing in this chapter. This is the dilation part. So dilation is a transformation. We've done transformations that slid a figure. I think we did ones, at least looked at ones that turn a figure. This is something that either enlarges or reduces the figure. Dilation. It's a transformation that changes the size of a figure, but not its shape. So we're going to do a little bit of enlarging or reducing. So see my blue arrow? I enlarged it to be the red arrow. And I'm kind of showing you the lines that we're going to use to help us get it bigger. We're going to be using a point out here and then draw through what we want to match up. We'll have to do some measuring with our ruler to get it to measure the right size. So it's really just going to be on measuring. Your book, I think, has color coding. I wish they'd made the first shape green, but I believe they did like I did up here. Blue was the figure you start with. Red is the one you stop on. Red, stop. So the red is the ending one. So is the red one bigger or smaller here? Bigger. Do you know what word you use to mean that it gets bigger? Well, it is a certain kind of dilation. Enlargement or reduction? Enlargement means getting bigger. All right, ready for the next screen? Okay, I think the next screen is about, it's about scale factor first. The scale factor, and we were just doing scale factor on our similar figures. Scale factor, again, compares the two sides. Now, the ratio is the one you stop on compared to the one you started with. And you actually don't even need side lengths. In your book, it's not going to give you the sides of the figure, but it's going to tell you how far from C to P prime, and how far from C to just P. And we can get the scale factor based on that. Yep. The CP prime is the one you stop on. The prime marking means that's the ending one. And CP is the one you started with. So if CP is 12, or CP prime is 12, and CP is 6, what's my scale factor to get the red shape? 12 to 6, which is 2 to 1. In other words, every side of this red one is twice as long as every side of the blue one. On the bottom example, CP, notice where the red one is? The ending one is smaller. Okay, so let's put this maybe 4, and this was possibly 8. So what's the scale factor to get the red shape? 4 to 8, which is 1 to 2, 1/2. The red one is 1/2 the size of the blue one. So depending whether you get bigger or smaller, the scale factor is either a big number or a fractional type. So here's what I was talking about, reduction or enlargement. think these are the last notes to write, and then we'll do some drawing. A reduction, that's a dilation where the image is smaller than the original figure. You remember when we talked about image and pre-image? Image is your ending, your stopping figure. Pre-image is the one you start with. So if the image that you end with is smaller than the original, that means your scale factor would have been like 1/2 or 1/3 or 2/3 or 3/4. If the scale factor is less than 1, it's going to make a smaller picture. If that scale factor is bigger, like 2:1, 3:1, 5:2, things like that, that's going to make an enlargement. The image that you end on is going to be bigger than the original figure. Thinking some of what we're going to measure might go more than 6 inches. We might need some of these longer. Okay, ready for the next screen? No, there's no right one. Okay, now are we done? No, still not. Gotta teach them speed writing. I don't know that shorthand is still used very much, but teach them shorthand. Okay, let's see, I think there's an example. All right, now control your rulers. Okay, we're going to do an enlargement and a reduction. And then you're going to do similar things on a worksheet as part of your homework.
Just for your homework. We're missing too many people. We're missing one. But each day, so counts as 5.
Okay, so you will find something real close to this picture on the sheet that I just gave you. We are going to use a scale factor of 2:1. Will that make the final drawing bigger or smaller? Bigger. Every side is going to end up 2 times what it was to start with. Okay, and we're going to use our ruler, and I'll do the best I can to show you up here. I can't really put my ruler up on the smartboard very easily. But you need to take your straight edge and draw from P through point T. Go out here quite a ways. Make it go right through point T.
Oh.
I'm going to have you measure in metrics because I think it's easier to multiply or divide that way rather than the inches. Make it go right through that point. Gotta go through that corner. Okay, now that you have that drawn, I need you to actually measure. How far is it from P to point T? Measure that using the metric side of your ruler. Go accurate to the nearest tenth. So the actual true measurement. Is it right at 3?
Yes.
centimeters?
Yes.
Yeah, probably. Okay, now to make it twice as big, we need to double that measurement. So 3 times 2 is 6. So now from point P, we need to measure out wherever 6 is. So we're going out twice as far. When we draw it, that's going to make the original shape or the drawing shape twice as big. If we wanted it 3 times as much, we'd multiply it by 3 or 4 or whatever. So we measured from P to T, and then we doubled it. So from P to, I'll put T prime right here. That's going to be the new point on our bigger triangle that matches with T. Now do the same with R. So draw your line from P through R. Measure how far it is from P to R. Take it times 2 and mark where the comparable point will be. P to R is how far. Is that 2.6 or 2.7?
2.7.
It's kind of debatable which one.
I want 2.7.
Okay, so whichever measurement you think, 2.7 or 2.6. We want to make it twice as big, so take that number times 2. So it's not exactly 5.5. Mine is 5.4. If you had 2.6 when you double it, it's 5.2. So again, from P, measure out to where your 5 point, in my case 4, where that is, that's going to be R prime.
And then we just connect the sides.
You will connect T and R. You want to do that now?
No.
Okay, so TR, that side matches with the original TR. Notice it's parallel to it, but it's twice as long.
It almost means the other side.
So what point do we still need? Q. Okay, so draw your line from P through Q. We go through Q. What are you going to measure? From P to Q, how far is PQ? Then we're going to double it. That is 4 centimeters. Okay, so 4 times 2, 8. So now with the ruler, mark out where 8 is. That's point Q prime. So finish making your triangle, connect Q prime and T prime. Connect R prime and Q prime. You should have a triangle that's bigger than the one you started with, but looks like it's the same shape. Okay, now in the next example, we're going to make it smaller. So instead of multiplying, we're going to divide. What's the scale factor I want on that second one though?
1/4. So like
1 to 4. So you're not going to divide by 2, you're going to divide by 4.
So then we go. We take
Okay,
P
anyone
and
still
R.
need this screen? Okay. So yes, you're going to line up P and like R. You actually don't have to go past it this time because we're going to make it smaller. Measure PR.
It's 9.9. No, it's
Do what? Yeah, I wouldn't make them real big, but yes, you can put dots on the corners if you want. Okay, P to R is 10?
Yeah.
Okay, so 10 divided by 4, 1/4 of 10 is? You have $10. What's a fourth of it if you're sharing it with 4 people?
Why would you share that?
2.5, so 2.5. So now from P, with your ruler, measure where your 2.5 is. And that's going to be R prime. Now, if you want to do one that's kind of easy to connect, go down. Going to S might be a little confusing. So let's go from P to U. PU. So P to U, how long is it? About 11.6. Okay, 11.6 divided by 4. 2.9. So line it back up with P. And mark U prime. It's supposed to be 2.9. Now if you connect R and U, does it go straight down? Notice that's the side that matches with that side of the rectangle. Okay, let's do PT. Same thing. Measure how far it is from P to T and do 1/4 of it. When you get your worksheet, be sure you use the actual measurements, the scale factor that I've stated on it. Don't use the same as this example worksheet. Okay, PT, I'm getting 14. Okay, 1/4 of 14. 3.5. So mark where 3.5 comes. When you connect your U and your T, notice that's making the bottom of your rectangle. It's 1/4 of the size it was. Which one do I still need?
Yes.
S. Okay. So from P to S.
It kind of looks like it's
Kind of looks 3D when you think of it a certain way. And I'm getting like 12.7 or 8, one of those two. 12.7 divided by 4 is 3.175. So 3.2 roughly. That's where it might be off just a little bit, but probably what you're measuring, it's going to be accurate enough. So when you finish connecting T prime, S prime, and R prime, are you making a little rectangle?
And then like the P dots, like you can make it another 4 smaller.
Okay. All right. So that's the type of thing you'll do on the front of the worksheet. The back of the worksheet I put pi, but you're going to enlarge or reduce. Yeah. This is on the homework worksheets that I have. Okay, so you're not doing a sample, I'm just showing you. But you're just going to use the grid to make it smaller and make it bigger. So how do you use the grid? Well, if I were to draw this arrow here, let's see, if I start here, how far do I have to go down to get to this corner? Go down 1, 2, 3 to the right 2. Down 1, 2, 3 to the right 2.
If I tell you 40 placements apply, do I have to do it?
If what?
If I tell you 40 placements apply, do I have to do it?
40 places of pi. Oh. I don't know. This is a different thing than that. So I'm just looking where they match up. This comes in one space. So go in one space, in one space. Then it went down 1, 2, 3, 4. 1, 2, 3, 4. across. So I've just enlarged that arrow. If this grid was smaller, it would make it smaller. So you're just counting how many spaces it is. That's the type of thing you're doing with the word pi and the symbol pi on the back. So I'll give you this worksheet and then I'll clarify the rest of what goes with it out of the book. I thought that you would use the ruler. You might need to take that packet though to complete this worksheet. I gave you the longer ruler in class. I don't think you need that long one for the assignment. But if you're using it right here in class, then you want to do it. So start measuring and drawing on that. Need one more? Can't count it without me. Or somebody kept two.
I bet Carrie kept two.
It was one.
Yes.
Okay, then the complete assignment is that dilation worksheet that you just got. And out of the book to go with that, 368. Six problems on 376. So out of the book is mostly the similar polygons. See if the angles match and the side ratios that match. All right, so that's the complete assignment.